All right, we're going to continue looking at acid-base salt solutions. Interesting. All right, we are going to be continuing to look at acid-base salt solutions, and this is kind of we're going to figure out how we can determine the pH of a solution based on the salt that results from the reaction of an acid and a base. Now, we previously looked at just the properties of a salt solution. So you have worked through something that looks like this. And you now know from what I have circled on this page, number 1, 2, 3, what type of solution to expect based on if the acid and bases are strong or weak. And this is going to be really important because it is going to help us determine how the salt in solution is going to react with water. And then that is going to in turn help us determine our pH. So we're going to dive right in with an example. And in this example, we have a sodium hydroxide and nitrous acid, which is HNO2. And it combines and we get a solution of sodium nitrate or sodium nitrite, sorry. And my children are getting a bedtime story right now, so it's a little loud upstairs. Sorry. Okay, so this is important because what we know is that this sodium nitrite is going to dissociate into its ions. So our sodium nitrite is going to dissociate into our sodium ions and our nitrite ions. Now, at this point, we have to put together a couple different pieces to kind of figure out how these ions are going to react with water. So the first thing to notice is that this NO2 negative is the conjugate base of nitrous acid. So it's a conjugate base of HNO2, which you need to recognize that in order for this NO2 negative ion to become HNO2, it has to gain a hydrogen. Okay. The other thing I want you to recognize is that you can use your work from our previous lesson to figure out how the ions from the salt solution are going to react with water. Because we looked at, when we go and look at this page, we looked at generalizations. So you can figure out if you're going to get hydrogen ions or hydroxide ions based on what you are dealing with. So we go back, and if we look at our base and our acid, sodium hydroxide is a strong. So we have a strong base, and our nitrous acid is a weak acid. So if you go back to our generalizations right here, you're looking at number 2, a weak acid and a strong base. So the ion that is going to come out of the negative ion coming out of the salt is going to end up creating hydroxides. So what we know then is that this NO2 negative is going to react with water and create hydroxide ions. The reaction looks like this. That nitrite ion is going, plus the liquid water, forms an equilibrium, and the NO2 negative acts like a base and accepts an acid, a proton, and we get HNO2 aqueous. And then what happens is the water acts like the acid and donates that hydrogen or that proton, and we end up with a hydroxide. So at this point, you now should be thinking, how am I going to get from this to a pH? And what you end up needing to do is you need to solve for hydroxide concentration. And you know how to do that because this is essentially an equilibrium. So you just need to put in an ice table, and you need to figure out how to solve for hydroxide concentration. So I have my ice table in here, and I'm going to put in what I need to. And remember that you actually do have an initial concentration of your nitrite because you have a 0.3 mole per liter solution of sodium nitrite, and that sodium nitrite dissociates in a 1-to-1. Here it is. So your initial concentration of your nitrite is going to be 0.30. Okay. Now you're starting with nitrite. So you know you are going to shift in a way to creating some products. So we are going to lose some nitrite. So it's going to be negative X. So our equilibrium is going to be there. Now water, we don't need to worry about. We're starting with 0 amounts of both products. So we're going to gain X of both of them. So now you have something that is tangible that you can solve for. You can solve for X to get hydroxide concentration, to then eventually get POH, and then you can solve for pH. Okay, so a lot of steps though to get there. What we have to do is set up an equilibrium expression to solve for our X. So you write out your equilibrium law expression, and I want you to note that I am using a KB. I'm using KB because I'm dealing with a conjugate base of I'm dealing with a conjugate base. Here we go. So you have to determine KB. And quite often KB is not given to you in a table of values. But what is going to be given to you in a table of values is a Ka for HNO2. So if it's not given to you, you have to go to the page of ionization constants that I gave you in an earlier lesson and reference that. And then you need to solve for Kb. So you should know that Kb is Kw over Ka. You can plug in the numbers. You also should know that Kw is 1.0 times 10 to the negative 14. And I'm looking up Ka for HNO2, and it is, you should see, is 4.6 times 10 to the negative 4. So you quickly do the math, and you get a Kb is 2.174, and you notice I'm carrying an extra digit. That's something that you should be doing as well. Actually, I'm carrying 2 extra digits, which is something that you should be doing as well. So I've solved for my Ka or my Kb from Ka, and then I'm going to sub in all my values into the equilibrium expression, and I'm going to go from there. Excuse me. So you sum in your values. It looks like this straight from the ICE table. And now this is looking like something that you definitely should be able to solve for. Now, you do not have a perfect square, but what you can do is check 100 rule to see if we can eliminate our x in the denominator. So we quickly do a 100 rule check, and we see that it is significantly greater. If we go through the math, we can see that it is significantly greater than 100. So therefore, we can ignore our x. So we can ignore this x, and then we can go ahead and we can solve for our x value. All right, so this is all the math working. It's working your way through. Pretty straightforward. You have done this before, but you get an x equaling 2.554 times 10 to the negative 6. So now at this point, you have a hydroxide concentration. You know that the concentration of hydroxide ion in the solution is 2.554 times 10 to the negative 6. So you can take this hydroxide ion concentration and now put it in a pOH calculation, because you know pOH is going to be negative log concentration of hydroxide. So you calculate pOH to be 5.59, and then such an easy calculation now to calculate your pH. So that's an easy calculation because your pH is 14.00 minus pOH. So we put that pOH of 5.59 in, and we get an 8.41. Okay, so then if you want strong communication, you're going to write your nice therefore statement to finish off this problem. Okay, so hit pause and copy. So the trickiest part to this question, to these types of questions, is understanding how the ions from the salt are going to react with water. What you need to do is look at if you have a strong acid or a strong acid, and if you have strong or weak acids or bases, sorry about that, and then looking over here at this page and going, okay, using number 1, number 2, and number 3 to figure out if you're going to get hydrogen ions or hydroxide ions. And then you write your equilibrium expression to reflect that. So you figure out if you're going to have the hydroxide ions here, or if it's going to be hydrogen ions based on what you learned in the previous lesson. Okay. Once you get to this point, after that, it's all what we have seen before. You might have to calculate Kb from Ka, but we have seen that before. Okay. So the trickiest part is to figuring out, using what you have learned in the previous lesson, if you're going to have hydrogen ions or hydroxide ions after this conjugate has reacted with the water. Okay, that's it for now. Give this a practice, and I think you will have a check-in on this.